All right, David Can here with another question bank question in topic 2.2 forces. The graph in the question shows the variation with t of the speed v of the ball, which has a mass of half a kilogram, that's been released from rest above the Earth's surface. So we've dropped it through the air, and we see how the velocity is changing. In the graph, we see that the velocity starts very small and increases over time, but the rate of increase is changing. So there's some sort of changing acceleration. The force of air resistance is not negligible. Assume that the acceleration of free fall is 9.81 meters per second squared. State, without any calculations, how the graph could be used to determine the distance falling. Well, we want distance. We're given velocity and time. Velocity is measured in meters per second. Time is measured in seconds. And we want to combine these two somehow to give us distance in meters. We've seen before that we can multiply meters per second by seconds to cancel the seconds and leave meters. And that gives us our hint, multiplication. So what we're doing is we're multiplying velocity and time, and when you multiply a height and a width, that gives you an area. So what we're looking for is the area under the curve. Now, one way to find that area, since this isn't a regular shape, would be to add up the boxes under the curve. Mercifully, the question doesn't actually ask us to do that. It says, without calculations, explain how you could do it. And so the answer is just to find the area under the curve. Part B says, in the space below, draw and label arrows to represent the forces on the ball at 2 seconds. All right, well, if the ball is in free fall, then it's being attracted to the center of the Earth, which means that there's going to be weight acting on the ball. We also know that air resistance is not negligible, so there's going to be air resistance acting in the opposite direction. But let's take a quick look at 2 seconds. At 2 seconds, the velocity is not constant. It's actually increasing, which means that the object is not in equilibrium. It's going faster and faster and faster downwards, which means that the forces on the ball are imbalanced. The weight is actually greater than the air resistance. So when I draw the air resistance, I'm going to draw it in the opposite direction, but I'm also going to make sure that I draw it smaller than the weight. To show that the ball is still accelerating downwards. Part 2 says to use the graph to show that the acceleration of the ball at 2 seconds is approximately 4 meters per second squared. So I've already talked about how I use the graph to find displacement. Now we're going to find acceleration. We have meters per second, velocity, and seconds, time, and we want meters per second squared. To do that, we'll divide. Now, if I divide a rise by a run, that's a slope. So that's my clue. That division here, this division is telling me that to get acceleration from the graph, I need to look at the slope. So I need to draw in a slope here. So I'm going to grab my ruler. You won't be able to see me do this, but I'm actually putting a ruler on the page to try and make this as precise as I can. As I draw in a tangent at 2 seconds. Okay. Now I want to use rise over run on this tangent to find that slope. How far up does it go and how far over does it go? Well, let's take a look. Let's take this point, since it's at 0 seconds, nice and easy to read, and maybe this one at 4 seconds, I think it's also pretty easy to read. And if I look at the geometry here, I think it should read out pretty well. We have a height, a rise, that's 5, 10, 15. And a run, 1, 2, 3, 4. Which means that the slope is rise over run. That's approximately 4 meters per second squared. 15 divided by 4 is not actually 4, I'm sure you recognize, but it's pretty close. Now, how close we would get to 4 would depend on how accurately we drew in our tangent and how accurately we read the graph. So there would be some wiggle room in this question. All right. Calculate the magnitude of the force of the air resistance on the ball at 2 seconds. All right. Well, going back to this diagram, we know that the two forces acting on the ball are the weight and the air resistance. So that means that the sum of the forces is the weight take the air resistance. At the same time, we also know that the sum of all the forces from Newton's second law is always ma, mass times acceleration. And we know what that acceleration is. We calculated it in the last problem. It's 4 meters per second squared. So actually, I know everything in this equation except for the force of the air resistance. That means that the force of the air resistance is going to be equal to the weight minus ma. The weight is the mass of the ball that was given to us. It's half a kilogram times the acceleration due to gravity. And the question told us we have to use 9.81 in this case. Take away the mass times the actual acceleration, which we found was 4 meters per second squared. This is going to give us about 3. When you do the question, you should use your calculator and then report to 3 significant figures. I was a little too lazy for that today. But I get 3 newtons. The last question says, state and explain whether the air resistance on the ball at 5 seconds is smaller or equal to or greater than the air resistance at 2 seconds. So going back to this graph, at 5 seconds, right here, is the air resistance going to be bigger than, less than, or the same as the air resistance at 2 seconds? Let's quickly draw in another tangent, just to get a rough idea. And I can see that at 5 seconds, the slope of the line is much less steep than it was at 2 seconds. What that means is that the force of air resistance is closer to the weight. Jumping back to this diagram, as the air resistance grows, it balances the weight better and better until finally they're in balance and there's no acceleration whatsoever. So this smaller slope, this smaller acceleration at 5 seconds is telling me that the forces are closer to being in balance. And therefore the air resistance has grown from 2 seconds to 5 seconds. So the answer is that it's greater than the air resistance at 2 seconds. And the reason for that is that as the ball travels faster and faster and faster, as its velocity goes up, it experiences a greater air resistance.